Yeah, I'll introduce you. Okay, so yeah, welcome back everyone to the final talk of this conference. So it's my pleasure to introduce Chongying Dong, who will talk about orbifold theory and modular extensions. So thank you very much.
Okay, first I'd like to thank the organizers for giving me this opportunity. And also I'm sorry to keep, I think, everyone late for dinner, for lunch, or for going to bed, okay? Let's see. So my talk will have 4 parts. The first part, I just give you a brief introduction. The second part will briefly recall the orbifold theory, and the third part, and also discuss something about the future categories and the modular categories. The last part will talk about how to use minimal modular extension to understand the orbifold theory. First, let's just see, okay, what is orbifold theory? Suppose V is a vertex orbital algebra, and G is a finite automorphism group of V. The orbifold theory tries to understand the VG module category. Here, VG is the fixed point vertex orbital subalgebra V. And the main difficulty in studying orbifold theory is the twisted modules. And there are no classical analog. So the twisted module is not a V module, but if you restrict to fixed point, it is a module for fixed point. In other words, in order to understand the VG module category, we have to study the twisted modules. The problem I mentioned already. So in general, we don't know how to construct twisted modules, except a few examples. We don't have general construction. Okay, for lattice VOE, or for some very special automorphisms, or for permutation orbifolds, people know how to construct twisted modules, but in general, people don't know how to construct it. So this is a problem in studying orbifold theory. What's going on? Okay. And then I want to mention, okay, a vertex orbital algebra is called rational. Maybe I think the people have used this concept or used this solution already in the conference. If the module category is semi-simple, okay, this is an analog of finite dimensional semi-simple solution algebra or finite dimensional semi-simple Lie algebras. But the VOE is very different from Lie algebra, because for semi-simple Lie algebra, we know there are infinitely many irreducible modules. But if V is rational, and there are only finitely many equivalent irreducible V modules. Then I want to mention orbifold theory conjecture. And if V is rational, then VG is rational. Second one is every irreducible VG module should appear in an irreducible twisted module for some G. And here are some results about this conjecture. Kanata Miyamoto in 2016 proved VG is rational if G is solvable and V is also assume V is also C2 cofinite. McRae proved part 1 if you assume VG is also C2 cofinite. In other words, you assume V is rational and VG is C2 cofinite. And we prove if you assume part 1 conjecture, then you can prove every irreducible VG module appears in your irreducible G-twisted module. The goal is to understand fully the VG module category, CVG. I always use CVG for VG module category in terms of minimal modular extensions. Here I want to recall a vertex orbital algebra V is called holomorphic if V is the only irreducible module for itself. Okay. Now I want to fix some notations. And we fix the G, we use HG to denote the set of holomorphic VOAs V such that G is a subgroup of automorphism of V. Then I consider all V holomorphic VOAs in HG, then there are corresponding the category, the VG module category, CVG. Here I use this equivalence, this braided equivalence classes. Then also I consider RG. RG is all the rational VOAs, such that G is an automorphism group of V. I also use S is an equivalence class of CVG for V and RG and up to braided equivalence. So I introduce this two set. One is A, one is S. A comes from holomorphic VOAs, and RG comes from the rational VOAs. In both cases, G is the automorphism group of these VOAs. Here, I just want to mention the main result. Suppose VG is rational C2 cofinite, then for every V in HG, CVG is braided equivalent to the module category of twisted drain field double dr by G for some alpha, for some 3 cosine alpha with coefficient in S1. Here S1 is a unit circle. 2, A is a finite abelian group as A is just a collection of all CVG where V is holomorphic VOA, and then this is a finite abelian group isomorphic to a subgroup of H3 GS1. The product given by this CVG times CUG just equal to CV tensor UG. We know if V is holomorphic, U is holomorphic, V tensor U again is holomorphic. And if G is the automorphism group of V, G is the automorphism group of U, then G is the automorphism group of V tensor U by diagonal action. And the third part is the A, this is the group, finite abelian group X on S. S comes from the rational VOA, CVG, but V is rational VOA with G being an automorphism group V. X on S freely with CVG, X on CWG, again equal to V tensor W, then takes fixed point the corresponding category. Okay, we also know this is, this is G again X on V tensor W. Last one I want to mention is that, okay, if alpha is, remember in our main, look at our main result, we only claim this is a subgroup H3, but we do not know this A equal to whole subgroup H3 GS1. But here I mentioned is if alpha is pointed, I will mention what is pointed, then there is this pointed definitely even unimodular lattice L such that G is the automorphism group of VL and CVLG is braided equivalent to the module category of the dr by G. So if for any pointed, I think 3 cocycle, we can realize the module category of twisted drain field double as a lattice, holomorphic lattice view, the corresponding fixed point in the module category. Here I just want to give 2 remarks. First, why category theory? Okay, and the birth of modern category theory, future category, model tensor category, and the vertex orbital algebras are almost at the same time. Vertex orbital algebra, the definition of vertex algebra was given by Bosch in 1986, and the category, this model tensor category, and so on, was given by Turaf in 1991. So basically, I think 91 or 92, at the same time. Of course, maybe I think for different purpose, but there's one thing in common. Both are motivated by trying to understand two-dimensional conformal field theory in mathematics. And the module tensor category or fusion category basically just collect the data given by Moreau in this famous paper by two-dimensional quantum field theory about fusion matrix, Brownian matrix, and so on. Second one is so-called reconstruction program, which says any modular tensor category can be realized as a module category of a rational vertex operator algebra. So it's natural to use the category theory to understand the Orbifold theory. Now
Sorry, can I just ask you a quick
this
question? Could you recall what it means for a 3 cocycle to be pointed?
Oh, okay. 3 cocycle is pointed, and if this Peter Drenfield double, this algebra, each representation is one-dimensional.
Ah, okay.
So d alpha g. So d alpha g, this d alpha g representation of this d alpha g is one-dimensional. Each irreducible representation is one-dimensional.
Okay. Okay. Thanks.
Sure. So it's just this corresponding module category. A category is pointed. Category is pointed means every irreducible object is a simple current.
Right. Right.
See, probably this is like a language like in view theory. Yeah, just every simple object is a simple current, or the dimension equal to 1. So first, let me briefly recall what a twisted module is. Suppose V is a VOA, G is a automorphism V of order T. Then here is the definition of twisted module. So M is 1 over T graded. Then it's just YM, this so-called twisted vertex operator, and then plus some axioms, this twisted Jacobi identity and so on. Then I will not mention, okay, because I'm not going to use it in my talk. If G equal to 1, we get a so-called V module, solution of V module. So if people are from, if you compare this one to the so-called type 2, type 3 alpha and cosmology algebras, and we know type 1, I think normal type 1 alpha algebra produce alpha VOAs. Type 2, type 3 alpha algebras produce twisted modules for type 1 alpha vertex operator algebras. Then I want to mention, if V is called G rational, if G twisted module category is semi-simple. In particular, V is rational if it is one rational. And V is C2 cofine if the subspace spanned by U minus 2V for all UV and V has C2V has finite codimension. And V is the CFT type if the dimension Vn equals I should say I should not say dimension. I should say Vn equals 0 if Vn less than 0, and V0 is one-dimensional spanned by the vacuum. Use Miyamoto-Callahan's result will show if V is rational C2 cofine, then V is G rational for any finite order automorphisms. If you need to use this AGMV theory to prove this result. Here, I just want to mention a result about the G rational. If V is G rational, there are only finite many irreducible G twisted V modules up to isomorphism. And each irreducible G twisted V module here is ordinary, namely the homogeneous space finite dimensional. And here is, in other words, M is you have this minimum weight lambda. Every L0 eigenvalue lambda plus n. We call lambda the conform weight of M. If V is also C2 cofine rational, then the Snell chart C and the conform weight lambda of any irreducible twisted module are rational numbers. Here is the main assumption in this talk. V is a simple vertex operator algebra CFT type, such that G is the automorphism group of V, and VG is rational C2 cofine vertex operator algebra. The conform weight of any irreducible twisted V module is positive except V. According to our assumption, the weight of V is 0. In other words, all other twisted modules have positive conformal weight. As we mentioned before, if G is solvable, the first assumption is equivalent to V is rational C2 cofactor. Now I just want to use SG is the equivalence class of irreducible G twisted V modules. S is collection of all twisted modules, and we know Gx on S in the following way. Fix GH in G. Suppose M is a G twisted module, then we can define new H inverse GH twisted V module M circle H. As vector space M circle H equal to M, and but the action is twisted by H. And then for every M in SG, we consider stable letter GM. In other words, we consider H in G such that M circle G and M are isomorphic. So this stabilizer X on M projectively, I use this projective action, I denote this projective action by phi H. Then, of course, then this phi H phi K equal to phi HK, and with extra factor, this 2 co-cycle, phi M, alpha M HK. Then we can define what's called twisted group algebra with a basis H hat, and the product is given by this 2 co-cycle. From discussion above, then M is a module for this twisted group algebra, and H hat acts as a phi H. And I use lambda M for the set of all irreducible characters of this twisted group algebra, and W lambda for the corresponding irreducible module. Then we have this result, okay? And then you can decompose M as a tensor product of W lambda tensor M lambda. Here, W lambda is the irreducible module for twisted group algebra. M lambda is a multiplicity space, but in this case, it's a irreducible module for VG. In particular, M lambda is non-zero for any lambda, Second one is M lambda and M gamma just are equivalent VG module if and only if lambda equal to gamma. We mentioned already this S, we have GX on S, then you can write S as disjoint orbits. In each orbit OGN, we select a representative MGN. Then M lambda GN for J and G lambda MG gives a complete list of inequivalent irreducible VG modules. So we know this all the VG module, how Ors give identification. From all twisted module, we classify all the irreducible VG modules. But we want more. We want to understand the VG module category and the tensor product and the Euclidean fusion rules and all other things. So now as we go to move to the fusion category. Here are fusion categories over C is C-linear semi-simple rigid category. C-linear means that every object is vector space and morphism space vector space. And it's semi-simple category with only finite many simple objects. And also the morphism space also finite dimensional. Then we have this unit object 1, and we have rigidities. Every object has a dual. Then we can, because this you have this tensor product, then we can have a Gruson-Dicken ring. Then of course you naturally has a product. Okay, so we have ring structure. I always use OC for the set of equivalence classes of simple objects. Then article of Nixich Ostrich in 2005 proof there is a unique ring homomorphism called Frobenius pair dimension from the Gruson-Dicken ring can C to R, such that the dimension of each object is bigger than or equal to 1. Of course, we assume object non-zero. And then when we use vertex orbital algebra theory, we realize Frobenius pair dimension is exactly the quantum dimension we defined later on. Then for a category, we can also define from B's pair dimension for the category, it is the square sum. Yeah, it's just a sum square for B's pair dimension of each simple object. Of course, here talk about equivalence class. And then we have so-called a breeding feature category. In this case, we have a breeding. This breeding is x tensor y to y tensor x. And also plus a lot of axioms. Okay, this axiom, I'm not going to use it in my talk. Then we can also have it's a reverse category. Reverse category C bar. So as a fusion category, C bar equal to C, but we use new breeding. New breeding, remember this breeding is a morphism. So C bar xy is cy x bar inverse, cy x inverse. So it's a new breeding. Then we talk about a breeding feature category is called a symmetric if C bar equal to C. In other words, if C xy times cyx is identity. Okay. Then we can also define the breeding equivalence. Okay. Basically, the functor from C to D preserves the breeding. Then we have so-called we have this symmetric feature category rep G. Given any finite group, the G module category is a symmetric feature category with normal with Euler tensor product. In this case, and the for B's pair dimension, just a Euler dimension. Okay. So this is just the classical result. Order of G equal to the sum of square dimension of irreducible modules. Then we also have this called pointed fusion category vector G alpha. Here alpha is arbitrary 3 co-cycle. In this category, each object is a G graded vector space, and each homogeneous subspace Vg is finite dimensional. Then we can define, in this category, we can define the tensor product. The tensor product still G-graded vector space, and the point G and the homogeneous space V tensor U is given by this one. Okay, the sum. In this category, the associativity isomorphism is controlled by this 3 co-cycle, this alpha GHK. Okay, and in this case, the simple objects just EG. Simple object just at a point G is 1 dimensional. In other position, just 0 dimension. So therefore, this is just 1 dimension. Okay, so it's just simple objects. And this one is appointed because this one is dimension 1. And again, in this case, from B's pair dimension of this pointed feature category equals order of G. Then we have a result by Delaney in 2002, which says any symmetric feature category is breeding equivalent to some rep G or rep GZ. We mentioned rep G already, but rep GZ as a feature category equals rep G, but with a new gradient, a new breeding, not gradient. Okay, new breeding. I'm sorry, not gradient. Okay, new breeding. And here Z is a order 2 central element of G. According to Schur's lemma, Cx on any irreducible module as constant. So because here we use Euler tensor product, so the breeding Cu tensor V equal -1 Mn V tensor U, because you can assume U in irreducible module, V in irreducible module, then Zx on U equal to -1 to M, and Zx on V equal -N. Then I think these 2 symmetric feature categories perfectly fit the view setting. Rep G for the vertex operated algebras and the holomorphic VOEs, and rep GZ for the vertex operated super algebras. Okay, I'm going to mention later on. Then I want to recall Milk center. Suppose C is a breeded fusion category, D is a subcategory. The Milk center is defined. You consider all Y and C, just CYX. This just composition CXY. This one is the identity X and Y. Yeah, for all X and T. This just a centralizer, the centralizer of D and C. Okay, this again is a breeded fusion subcategory of C. The Milk center is the centralizer of C in C. That's all element, you call the all object, commits every object in C. This is called Milk center. Then C called the non-degenerate. If the Milk center is just generated, is equivalent to the category of vector, category of finite dimensional vector space. In this case, generated by 1. For the category generated by 1 equivalent to the category of finite dimensional vector space. Of course, here I just want to see the modular if it's spherical and non-degenerate. And spherical, you can define trace, left trace, right trace equal, and so on. I will not go detail. And it's modular because the modular group SL2Z acts on a gross deco range KC. Then I want to recall Dreyfus center. For any fusion category, you can define C, you can define Dreyfus center. And this C may not be breeded, but Dreyfus center ZC is always breeded. And for this pair dimension of Dreyfus center is for the square of for this pair dimension of C. And also the pointed fusion category vector G alpha, for this pointed fusion category, the corresponding Dreyfus center is always modular tensor category. And also the Dreyfus center of rapid G is also modular tensor category, which is breeded equivalent to Z vector G alpha with alpha equal to 1. Okay, this is also, yeah, these two are breeded equivalent as a modular tensor category. Now I want to recall Dreyfus double. Original Dreyfus double is for Hopper algebra tensor is dual. Of course, we know if you find a group G and CG's Hopper algebra is dual with also Hopper algebra. Motivated by the Orbifold theory, G-Graph, Pasquier, Rocher in 1990 defined so-called twisted Dreyfus double d alpha G. As a vector space, d alpha G equal to CG tensor CG alpha. Here alpha is a 3 cocycle. But the product and the co-product in this case are modified by alpha or just controlled by alpha. Use this alpha define product and product and co-product. And then it's D-graph Pasquier Rocher's idea. If V is holomorphic VOE, G is finite automorphic group of V, then there should exist alpha such that the category of VG model category, VG model category of VG is equivalent to the D alpha G model category. Of course, back then, when they made this, I think, setting, there were no module tensor category, the language of module tensor category was not available. But the really means use model language. It's this VG, CV, the VG module category, CVG, and the G alpha G module category, they are equivalent as the module tensor category breed equivalent. And also I want to mention, and the module category D alpha G and the Dreyfus center for vector G alpha, these two module, this module tensor category and this Dreyfus center, these are breed equivalent. Then I define what's called a module extension. Right now I use epsilon, I use E for rep G. C is called a E category. If C is a breeded fusion category, and E is a subcategory such that the Milk center of C is exactly E. M is called a minimum modular extension. First, M is a modular extension of C. In other words, C is the subcategory of M. You have embedding. Second one, the forbidden pair dimension of M is the order of G times forbidden pair dimension of category C. Then you can define two extensions are equivalent. Here I just don't. Yeah, you have some functor. You have functor with a certain property or not. Then I use this MECT. This is a set of equivalence class of minimal modular extensions of category C. Okay, this is a set. Then Muger in 2002 conjectured this set is not an empty set. Okay, and but in more general setting, okay. But there's current example by Greenfield, some C does not have modular extensions. Therefore, there are no minimal modular extension. But this is never published, and people, I think, talk about this for a long time. Okay. And also this set, you have this equivalence class, and but how big this set is, and according to result by this, Brillard and Rowell and Wang, according to the result, this set is always finite set. Up to Brillard equivalence, is always up to this equivalence, is always a finite set. This is a finite set. Now I recall regular algebra. Suppose C is the Brillard field category is a regular algebra in C, and there is this there is this commutativity and all separable conditions. Okay. Then for algebra A, and you have a notion of A module and a local A module. Okay. I use CE for the A module category in a C, and C is 0 for the local A module in category C. Okay, and of course CE0 is a subcategory CE, and in this case CE again is future category. CE0 is the local module category is a Brillard future category. If C is a module tensor category, then the local module category again is modular. According to Chiral Ostrich result in 2002, every regular algebra in category E has a form. It's just the dual of H over H, H over H, H for any H subgroup. In this case, for this algebra A, let's see, for this algebra A, the A module category, local A module category just equals rep H. Okay. But I want to, this result is basically correspond to the my result with Jeff Mason and Haisheng Li about the GAR correspond between subgroups and sub-VOEs. Here basically a similar thing. Okay, now I need to define so-called relative product. The first one, and for any two Brillard fusion category C and D, you can define the tensor product. This is called the Delin product. Okay. Then for this, we have so-called reverse category for any fusion category C, we have reverse category C bar. Then there's so-called canonical regular algebra. This just you consider simple objects X tensor X star because we assume C is rigid. There's dual. Okay. This consider this sum. This is a regular algebra. This is a tensor category. Right now, suppose C and D are Brillard E categories. Then LE is a regular algebra in E tensor E bar. But because E is symmetric in E tensor E, but E is subcategory C, E is subcategory of D. So this LE is a regular algebra in C tensor D. As a result, we can define relative tensor product C tensor epsilon D equal to just because this is regular algebra here, you can say local local L E module category. Okay, so this is just a so-called relative tensor product. Then you have this theorem. The theorem says the minimum module extension of E exactly equal to all these geometric centers for pointed fusion category VEC G alpha. In fact, this one is an abelian group, and with the product, this product is relative tensor product. Yeah, this called relative tensor product over E. This is, as many people have made a contribution to this result. Miguel, Kirillov, Drenfield, Gelaki, Niksis, Ostrich, Lan, Kong, Wen. Okay, and then is if C is a bridge field category whose Drenfield center, whose Miguel center is E, then the equivalence class of minimal module extension of C is a tensor for this minimal module extension of E. Again, with the action, again with this E, relative tensor product. Tensor means the action is free and transitive. Okay. So in other words, the cardinality of this minimal extension of C, this set equal to also the order for just equal to cardinality of minimal extension of E. Okay, now we can move to the Orbifold theory and the modular extension. Suppose right now V is a vertex orbital algebra. G is a finite atmospheric group of V. Assumption is VG is rational and C2 cofactor I just mentioned. Okay, I use this notation already. CU U module category for any vertex orbital algebra U. This is a result of Huang, which says the module category CU for any rational vertex orbital algebra U is a module tensor category. I forget about the other assumptions. Okay, just make a statement simple. You C2 cofactor and V also self-due and so on. But I just use rational VOEs. Okay. And now we just recall result. Okay. But we saw our early result. Okay. I use the irreducible G for the irreducible category of G. Then for any lambda, for any irreducible category of G, W lambda is corresponding irreducible G module. Then we have this Schur duality decomposition, and V lambda, W lambda is the G module, V lambda irreducible VG module. And also all these VG modules, are equivalent. Now I consider EVG be the subcategory of CVG generated by V lambda for lambda in irreducible G. Okay. Then we prove this EVG is a symmetric fusion category which is briefly equivalent to rep G. This is equivalence given by this function given by F maps W to hom VG W prime. Here W prime is I should use the dual to V. Okay. In particular, and use this equivalence F because CG star is a regular algebra in rep G. This regular algebra is this corresponding F maps this regular algebra to this one F CG star is a regular algebra in CVG EVG, and this is isomorphic to V, and V is a regular commutative algebra in EVG. Okay, so this under this functor is F map this regular algebra in rep G to a regular algebra in EVG, and it's isomorphic to V. Now I just give more assumption. Okay, assume V is rational and G is finite atmospheric group V. We just mentioned. Okay, then V is a regular commutative algebra in EVG. EVG is a subcategory of CVG. Now I use okay, and because V is a regular algebra in VG module category, so I can have a V module in a VG module category, CVG. Okay. Then also in the VOE setting, we have a GT V module category for every G. Then I consider the direct sum of all GT V module category. Okay. Then we have a result which says this CVGV and these two categories are the same. Okay, are same. In particular, this CVG category with regular algebra, local module just a category V module, and or CV1. Okay. From category theory, we know the tensor product G-tensor module and the H-tensor module is a G-H-tensor module. But we do not know how to define 20 operator among tensor modules in terms of Jacobi-like identity to give tensor product of series vertex orbital algebra unless GH commute. If G and H do not commute, you can still define the tensor product using the correlation function, but there are no Jacobi-like identity, okay, to define 20 operators. But in category theory, if you have G-tensor module, H-tensor module, you can define because future category, you can define GH. Their tensor product. Okay, the tensor product is a GH tensor module. So this connection make our life a little bit easier. Now I just want to mention, okay, and this H is homomorphic VOEs and G is above group of V. First, if V is homomorphic, then CVG is a minimum module extension of EVG or E, because E and EVG are equivalent. In particular, CVG equivalent to the D alpha G module category for some alpha. The second one, and the CVG or this category is equivalent to this this category. Okay, this is pointed future category. This is pointed future category. Okay, these are all twisted modules. We know this all twisted modules has dimension 1. Okay, so this is pointed future category equivalent to V alpha G alpha. Okay, and we have category theory. We have this relative tensor product. Okay, we have two categories. We have relative tensor product. We prove this relative tensor product is equal to simply in VU setting. You can just use this U tensor V. Okay, this is Newholm VOE. We just mentioned this one. These two operations are the same. Okay, this one is a relative tensor product in category theory. Here is just a VOE tensor product. Then you consider all the CVG with homomorphic in HG, and you consider equivalence class. This one is finally Abelian group as homomorphic to a subgroup H3 GS1. And with this product, at this point, we cannot prove this whole group, although we believe it's true, but we cannot realize every module category D alpha G as CVG for some homomorphic VOE. Here I just want to mention the identity group. Identity of this group is a CVG with alpha equal to 1, which is pretty equivalent to Jethro center Z epsilon. As I mentioned, it is expected that the categorical minimum module extension set should equal to homomorphic VOE, minimum module extension from homomorphic VOE. Another thing I want to mention is about the inverse. In category theory, the inverse of CVG is the reverse. It's just reverse of CVG. But VOE theory, okay, and the inverse is just if the order of this category is O, then you can this category bar equivalent to CV tensor n-1 to G. But in general, it's very difficult to find the inverse in VU setting. But for some examples, we know how to find this inverse. Last one just reformulate the result before. I don't want to. It's not so important. Just you don't forget about categories here. You can see this is a group and so on. This Holomorphic VOA HG is a group, with this tensor product. And it's a finite group. Now we just consider rational VOEs. For rational VOEs and RG, we mentioned this already. G is the automorphism group V. Then I use solution FG. FVG is subcategory CVG generated by VG submodules, V modules. You consider all V modules, not history modules, only all V modules. And then you consider the sub VG submodules. This generate a subcategory called FVG. And then we have this the following result. Then FVG is a British future category such that its milk center is epsilon VG or epsilon. So in other words, FVG is an epsilon category. Then the corresponding VG category, module category, CVG is a minimum module extension of FVG. Then you can have use vertex orbital algebras. You can consider the equivalence class of minimum module extension of FVG. This is CWG, WRG, and the FVG and the FWG are equivalent. Again, this one's final set, and the group is minimum module extension epsilon. This MVEXT X on this set freely. The actually again use this tensor product. Okay, this is just a relative tensor product in category theory, just equal to this new product given by the tensor product of VOEs. I think this is just similar to the previous result. So this says Milger conjectures holds for FVG. Again, it is expected, and the minimum module extension of FVG from category theory and or from the VOE theory should be the same. And here is a picture I want to see. If you consider V module category, okay, you have V. The category generated by V is equivalent to the category of finite dimensional vector space. This one is subcategory of this one is a subcategory of V module category. V module category is all the pieces included all the module category. Then you just restrict to each category to the fixed point origin. Each one is a V module. You restrict to VG, you restrict to V, because for example, you restrict to V to VG, you get a lot of VG modules. This generates a subcategory called EVG. This is just equivalent to E. You consider all the V modules restrict to VG, you get a category called FVG. Then you restrict all the V modules, you put twist modules, you get all the you get a so-called VG module category. Okay, so this is just a connection. Now, last I just want to mention super orbifolds and modular extension. The discussion above also applies to vertex orbital super algebra V with finite automorphism group G containing the canonical automorphism Z coming from the superstructure. Here Z is the central element. And in this case, epsilon VG, EVG, you can consider super VOE, EVG, and the rep GZ are equivalent. If V is holomorphic, then CVG is the minimal module extension of rep GZ. Okay, but I want to mention, and in the category theory, and the minimum module extension of rep GZ is not known at this point, except a few examples. So I think a super VOE structure may provide a tool to construct a lot of examples, minimum module extensions for rep GZ. And in general, and the FVG is breeding the rep, you have epsilon G category. This epsilon is a rep GZ category, and the CVG is the minimum module extension of FVG. And more in progress, we have not finished writing of this paper. So that's all for my talk. Thank you very much for your attention.
Okay, so are there any questions? Maybe on Zoom? So maybe I could ask just a very naive question.
Okay.
So when you look at fixed points in a holomorphic vertex algebra, so if the group is cyclic, then it's easy to read off the cocycle, the 3 cocycle from the conformal weights of the twisted modules, right? So
Yes.
in general, somehow group homology could be much more complicated, but to what extent do you think, is there some way to read off a cocycle from things like conformal weights or T-matrix?
Okay, but I think the problem is, it's because here this 3 cocycle really, you consider all the G-twisted modules. You consider G-twisted modules. This one, from category theory, we know this is a fusion category. So you have G-twisted module and H-twisted module, you have tensor product is a GH-twisted module. But this 3 cocycle, I think right now we cannot read this from view theory. You can only read this from category theory, because the positive fusion category, the associativity is this 3 cocycle. You have this 3 cocycle is just tell you how the 3 twisted modules, how you perform the tensor product 3 twisted modules.
So in some, maybe in some sense it goes back to that problem that you said, that it's not known how to define directly tensor products between different non-commuting twisted modules.
Yes. You have a G-twisted module, H-twisted module, and a K-twisted module. This 3 twisted tensor product, the associativity is given by this 3 cocycle.
Okay, thanks. Yeah, it's very interesting.
Sure.
Any other questions? Okay, so I think there are no further questions. So, certainly let's thank the speaker again, and indeed thank all speakers during this conference.
Thank you all the organizers.
Yeah. You what?
Yeah, I want to take this opportunity to just thank the organizers, and in particular Jethro, who was like the main organizer of this event. I think we owe you a great deal of gratitude for this, so a round of applause.
Thank you so much, and yeah, I mean, thank you all so much for coming. I think it's been a great event. I mean, it was very sort of somehow uncertain how many people would be here in person, and in the end, I think it's been really good. So, yeah. Sorry? Oh, yeah. So we'll send an email about this, but for those who are staying for the short courses starting next week, they begin at 9 o'clock next week on Monday. As I say, we'll send an email about this too. They won't be on Zoom, but I think they will be broadcast on YouTube. So, yeah, it will be possible to watch the talks as well on YouTube. I don't think there are any other announcements. One of the other organizers has an announcement they want me to make. Let me know. But otherwise, I think that's it.
And the talks will be every day, so start at 9?
No.
So will be
Monday, Wednesday, Friday.
Monday, Wednesday, Friday. Okay.
Yeah,
so
9
on
o'clock.
Thursday there will be